Refraction through a lens. The previous chapter was refraction through
Light.
what? Refraction through
Plane mirror.
plane surface. Okay, and this is lens. Now, what's the difference between plane surface and a lens? Both are transparent. Plane surface is also transparent. Yeah, it's about curvature. Okay, plane surface was the reflection was happening through a flat surface. Okay, so the light was coming in like this and it was bending either towards the normal or away from the normal. Okay, the thing is the surface was plane. In this chapter, the surface is not plane, it is curved. Okay, so the curvature is either like this, outward, or it is inward. Okay, 1 minute. Okay, so glass structures which have curved surfaces, they are called lenses. Right. So you have two types of lenses. One is a convex lens and one is a concave lens. Okay. A convex lens is where it is bulged in the center and tapered towards the edge. Tapered means narrower towards the edge. Okay. So these lenses in this picture you have seen, in all of these three examples, the middle portion is thick. So these lenses are called convex. Shape can be anyhow. The condition is what for a convex lens? The center part should be thicker than the edges, the borders. Okay. And the second type of lens is a concave lens. Concave is like a cave inside, right? So in the concave lens, the middle portion is how? It's
Narrower.
narrower. And the borders, the outer portion is thicker. Okay, so
Yes.
two types of lenses. Now, what does a convex lens do? Before that, there are three types of convex lenses. Biconvex means both the sides it is bulging outward. Plano-convex means one side it bulges outside and the other side it is flat. But overall, you see the middle portion is thicker. And then a concavo-convex means one side it looks like concave and the other side looks like a convex. But it's still a convex lens. Why? Because the middle portion is thicker than the borders. You understand? The shape of the lens from both sides could be anything. You see, it could be bulging outward, it could be flat, or it could be bulging inward. But all of them are convex. Why? Because the middle part is thicker than the edges.
Thicker than the edges.
Is that clear, everyone?
Yes, sir.
So just once again, convex lens is thicker at the border. That's all you need to understand from the first part. Convex lens thicker in the center, and at the edges it is tapered. Okay, tapered means it becomes narrow. The second type of lens is what? Concave lens. Why is this concave? Because the middle portion is thin and the edges, top and down, is thicker. Now again, there are three types here. Biconcave means both the sides looks like it's concave, means it's going inside. Plano concave means what? One side is flat and the other side is concave, going inward. And convexo concave means one side looks like convex, it's bulging outward, and the other side is concave, it's going inside. Okay, but all these three are concave. Why? Because at the middle it is narrow and at the edges it is broader. Okay. Now, if you take a lens, like say a convex lens, and if you cut it into pieces, each of these parts looks like a prism. Imagine the sides is not so curved, but it's all flat edges at all these points. So each of them looks like a prism. What is the property of a prism? The two flat edges on both the sides are at an angle. That's how a prism is, right? See, instead of being two flat surfaces on both sides parallel to each other, the two flat surfaces are at an angle. That's when you get a prism. So if you see a convex lens or a concave lens, you see each of them, their two sides are not parallel to each other. They're at an angle. So in other words, a convex lens is like multiple prisms. Same way, even a concave lens. Concave lens is like multiple prisms because the two sides, opposite sides, are not parallel to each other. So let's cut a convex lens very sharp and make it like proper prism on top and a prism at the bottom. Okay, now what will happen to a light if it enters inside? Okay, let's take this as a prism on top. Then the middle portion will keep it as parallel to each other, and the lower portion will again keep it as a prism. So let's take three rays of light. The first ray of light, say it starts from the same point. Okay, it goes like this. One goes like this. Okay, let's see the first ray. So think of it as a prism. What happens to this ray? It goes like this and then it bends downward. This is how we saw in a prism. A light that's going down, it will bend like this and then go like this. Yes? And if a ray passes through a flat surface, it keeps going perpendicular and it keeps going without any deviation. So these are three
Yes.
seen in the previous chapter. Correct? So this is what happens even in a lens. So now curve the whole side properly. Okay. And if this is the light source over here, okay, if there's a ray of light that's going up, what happens? It becomes parallel here, then it goes down. Here also, this one, how it goes, keeps going straight without any deviation. And the one that's going at the bottom, it'll go here. It'll refract one point at one place, and then again it'll refract. This is what actually happens in a lens. Okay. But when we draw the lens, we don't show two refractions taking place. That is actually what's happening. Right, there's one refraction at the left side surface and one refraction at the right side surface. How do we draw it when we draw? Okay, how we draw is we just draw the straight line to the center. Imagine there's a line that's passing from this corner to this corner of the lens. So you draw one ray, how? Straight to the center line, and at the center line you will bend it. Even though that's not actually what's happening, this is how you're going to draw it. Same way for this, if there's a light ray going down, don't bend it at the surface, go to that center line, and here you will bend it. This is how you're going to draw it, not like this. Which is the correct way? The top one is actually what's happening, okay? But you will show it like this, just to make it easier, to make the diagrams easy. Okay, so just draw these. These are three diagrams. The top one is the simplified version, showing you how the lens can act like a prism. Second one is actually what's happening. And third one is how we're going to draw it. Heading is convex lens. Ahmed, Nathan, done drawing this? Okay, we'll see the same thing for a concave lens now. So concave lens, we will only draw one diagram now. How do you draw a concave lens? Okay, I'll show you the right way to draw the concave lens after explaining some words. For now, we'll just draw it. Okay, like this. A line passing through the center. Okay, forget the line. So if there's a ray of light now, see in your book, instead of drawing one ray from one point, one point source, they're drawing three different rays parallel to each other. Okay, and we can see that all these rays, they will meet at this one point. What do we call that point as? We call it as the focus. Now, this is what happens to three parallel rays of light when we see a concave lens. So what happens? They all move away from each other. All the rays diverge. Here, what's happening to the rays? They meet at a point that word is called converge. So convex lens is called a converging lens because it converges all the beams of light, rays of light. It gets them to one point. This is a concave lens. What does the concave lens do? Diverges the ray.
Diverge. Yes.
It's called a divergent lens. See, in the beginning, they have written here the lenses. Convex lens is also called converging lens because it converges the light, brings them to one point. Concave lens is called diverging lens because it diverges the rays of light, separates them. So here we see in a converging lens, where are these rays of light meeting? They're meeting at this point called the focus. Where are these rays meeting? They're not meeting anywhere. They're going away from each other. So do they meet anywhere? Where? If you extend these line backwards, they meet at a point. You see, how is the ray actually moving? It's going this way, right? But if you draw these rays backwards, they're meeting at a point. That is where the focus is. So in other words, for a concave lens, the focus is on the right side of the lens. In a convex lens, the focus is on the left side of the lens, behind the lens. So is the light actually going to this focus for a concave lens? The light is not going there at all. It's an imaginary focus, not a real focus, focal point, because the light rays are not going to that point. Here, in a convex lens, the focus is the real point because the light is actually meeting at that point. Everyone clear about this concept? In a convex,
Yes, sir.
the focus is the real point because light is actually meeting over there. In a concave lens, it's an imaginary point. The light rays appear to come out of that point. They're not actually meeting over there. Okay, now let us look at some terms. When we draw these diagrams, there are some words. Okay. So this blue color part here is the lens. If you see, this lens is actually part of a ball, a sphere, a spherical glass piece. It's like they took a spherical glass piece, spherical sphere. You know what's a sphere or a sphere? It's a ball-shaped structure. So if you take a glass that's in this particular shape, and then if you carve out, if you cut a piece of it, you will get a lens. Okay. So the center of this circle, of which the lens was originally a part of, the center of that is called this center of curvature. What is center of curvature? It's the center of the sphere of which the lens was a part of. Maybe it was not part of it. They made it just like that. But it's an imaginary sphere that you have to imagine. And the center of that sphere is the center of curvature. So now there are two surfaces. See, surface 1 and surface 2. Surface 1 has its center of curvature on the right side, and surface 2 has its center on the left side. So there are two center of curvatures on both the sides of the lens. Now in this diagram that they've given, you see the first surface is more gradual, and the second surface, it's more curved. So you see the left side circle is smaller than the right side circle. Do you get that? But in all the lenses that you are drawing, you will always draw equal curvature on both the sides. So the circle that forms on both the sides will be equal circles. Okay. All right. Next word is the distance from the center. O. Okay. What is O first of all? O is called optical center. It is the center of this lens. Now the distance from O to C is called radius of curvature. What is C? C is what? Center of curvature. And OC is radius of curvature. Again, what is C? Center of curvature. OC, that gap distance from OC, that is radius. Like a circle. No, a circle has radius. Normally radius is from where to where? We go from the border of the circle till C. But here it is from O to C. That is the center of, sorry, that is the radius of curvature. Then this line that passes through both the center of curvature is called principal axis. Okay, and then there's one point here which is not written here, which we saw before. What is that point? F, the focus. Okay, so where does focus come in all of this? The focus comes exactly between O and C, coincidentally. Okay, so If this is your lens, okay, what is this line called? Principal axis. This principal axis passes through this point. What is this point here? O, optical center.
Oh,
And this point here,
center of curvature.
center of curvature. Okay, so right in between O and C, what do you have? Focal.
Focus.
Yeah, focal point. The point is called focal point. Okay, now we have two distances. One distance is from O to C. What do we call that distance? Radius. Radius of what?
Yes.
Radius.
Up here.
Radius of curvature.
Radius of curvature.
We also have a distance from O to F. That distance is called
Focal length.
focal length or focus. Focus or focal length. This point is called what? Focal point. Okay, a few conditions. When does the light not deviate? So we drew three rays, a ray going up, a ray going through the middle, and a ray going at the bottom. Out of these three rays, which ray does not deviate? The middle
The
one,
middle.
right?
Yes.
So the condition is if a ray passes through the optical center, it will not deviate. Okay, it just has to pass through the optical center. It can go even like this. See, at an angle. If it's passing through the optical center, it will not deviate. Is that clear? So here you can see a diagram. This ray is passing through optical center, no deviation. Even for a concave lens, it's passing through the optical center, there is no deviation. In reality, if you see, there is actually two deviations taking place. See, this is the actual diagram. So at the first surface here, there's a deviation. It bends towards the normal because it's going from a rarer to a denser medium. The light bends towards the normal. And then at the second point R, it is bending away from the normal. So actually there are two deviations, but the thing is the incident ray and the emergent ray are parallel to each other if it passes through the optical center. For simplicity's sake, what do? We just show it like this. We don't show the two deviations. Is that clear? Confusing or not? No. Is it clear? I'll say that again. This is what's happening in reality. When a ray passes through the optical center, this is what's happening. There are two deviations, but the incident ray and the emergent ray are parallel to each other. And because of that, we just ignore that and we just draw it like this. Through the center, no deviation at all. In the previous chapter, what did we call this? Where the incident ray and the emergent ray are parallel to each other, but it's slightly moved away. What do we call this? Lateral displacement. Okay. So there is a lateral displacement when the light passes through optical center, but we ignore that. And we draw it like this. Clear now?
Yes, sir.
Anyone has any doubt? Okay, now going back to a diagram that we drew. Okay, so we'll draw it again for a convex lens and a concave lens. For a convex lens, parallel rays of light. What happens to parallel rays of light? They will meet at a point. Yes? What do we call this point? Focal point. Okay, but we don't just name it as focal point, we call it F2, second focal point. Okay. So this is a what is this lens? Convex lens. So on a convex lens, see the parallel rays of light, they meet at a point called f2. Now a concave lens. Okay, in a concave lens also we'll draw parallel rays of light. What happens to these rays of light? They will, what's the correct word? Diverge. Okay, they will diverge. Okay. So where do they actually meet? Backwards, right? If you draw these lines backwards, they will meet at a point. That point is also called f2. Okay. So you see, for a convex lens, f2 is on the right side. And for a convex lens, sorry, for a convex lens, f2 is on the right side. And for a concave lens, f2 is on the left side. So how you need to remember this is, look at the incident rays. In both the cases, the incident rays are how? Parallel to each other. Okay. So when the incident rays are parallel to each other, the point where the light rays either meet or appear to meet is called f2. Is that clear what's f2? Okay, let's read the definition for f2. So you have two definitions, one for convex, one for concave. For a convex lens, it's called the second focal point. F2 is called what? Second focal point. So the second focal point is the point F2 on the principal axis of the lens, such that the rays of light the incident rays are parallel. See that the rays of light incident parallel to the principal axis after refraction from the lens pass through it. So what they're saying, the incident rays are parallel to what? Parallel to the principal axis. Middle line is called the principal axis. After passing through the lens, they get refracted and they meet at that point. That point is called the second focal point. In our own words, how a second focal point? If the incident rays are parallel to the principal axis, after refraction, the rays will meet at second focal point. Same way, what will be the definition for f2 for the concave lens? Incident rays should be parallel to principal axis. After refraction, the rays appear to be formed or appear to be produced from second focal point. The rays parallel, they will diverge, but they appear to be diverging from one point. That point is f2. You
So,
understand?
so for a concave lens also you have to draw that middle line. Like
Middle line is
how we
principal axis. Oh, this line. This line? That's what he's
yes,
saying, right?
sir.
Yes, this line has to be drawn for every lens. Okay, concave or convex, because that is where you show the bending taking place. Okay. All right, let's read this definition once again. Beryl, read this definition loudly.
For a convex lens, the second focal point is a point F2
On the
on the principal axis of the lens, which
such that
the rays of light incident parallel to the principal axis after refraction from the lens pass through.
Little confusing here, but you understood the meaning, right? The incident ray should be what? Parallel to the principal axis. So after refraction, they will meet at that point. That point is the second focal point. Next, for a concave lens, let's look at this definition. Leah, read this definition. So this is F2 for what? Leah, what happened? No voice? What happened to voice? Marching too much. You won't read.
For a concave lens, second focal length is a
Second focal point, slowly.
second focal point is a point F2 on the principal axis of the lens such that the rays of light incident parallel to the principal axis after refraction from the lens appear to be diverging from
Yeah, these rays appear to be diverging from this point. See, that's the difference. The incident rays are parallel to the what? Principal axis. And after refraction, what happens to these rays? They diverge. As if they're diverging from where? From that point. That point is called this second focal point. Is that clear, everyone? Clear? Is it clear? Okay, draw these two diagrams for a convex and a concave. What is F2? And also write the meaning of F2 definition in your own simplified language. Start with incident rays are parallel to each other. That is the main point. So how do you know F2 for sure is in both, whether it's a convex lens or a concave lens, the incident rays are parallel to the principal axis. So now we'll see what is F1. So in F1, what do you think will be parallel to each other or parallel to the principal axis? Okay, look. Okay, this is the principal axis, this is the convex lens. Okay, here how it is, no? If this is one ray, then another ray is on the principal axis, and this is another ray. Now these rays will go parallel to the principal axis. So this point here is F1. I'll say this, I'll explain it. If rays of light are passing through this point, after refraction, they become parallel to the principal axis. So that point from where they started off is the first focal point. Okay. Let's read the definition from the textbook. Okay, listen. For a convex lens, what we have drawn, the first focal point is a point F1 on the principal axis of the lens. Right? Obviously, yes. Such that the rays of light, what? Coming from it. See, if there are rays of light coming from it, imagine this is a bulb. So the rays of light that's coming from it, after refraction, what happens to the ray? After refraction through the surface, what? Becomes parallel to the principal axis. You understand? So here the parallel rays are on the right side when we're drawing F1. How about for this now? Here where F1 will be? It will be on the right side. Okay. So again, you know that F1 is on the right for sure. You also know that the rays that are coming out on the right should be parallel to each other. So how will the rays be here? So the ray should be pointing straight towards F1. If you draw dotted lines, they should be going straight to F1. Second ray also, see straight, it should be going pointing towards F1. So this ray, they will what? Diverge. So they're bending away. They're coming towards, but they're bending away. But they become parallel to the principal axis. Even this lower ray, they're supposed to go straight, but they bend away. And they become parallel to the principal axis. So this point is F1. Let's read the definition for F1 for a concave lens. Okay, I'll read, listen, while listening, you look at the diagram. For a concave lens, the first focal point is the point F1 on the principal axis. See, always say that first, it's on the principal axis of the lens, such that the incident rays of light appearing to meet at it. See, the incident rays are where? They're appearing to meet. They're going straight towards F1, appearing to meet at it. After refraction from the lens, what happens to it? They become parallel to the principal axis. Do you understand? Incident rays are appearing to go to the F1. They're appearing to meet at the F1. After refraction, they become parallel to the principal axis. Okay, so we have seen 4 different diagrams here, right? F2 for concave and convex, F1 for convex and concave. Okay, and you see F2 is right side, here F2 is left side, here F1 is left side, here F1 is right side. So how do you not get confused? What's the main thing you need to remember for F2? Incident rays are parallel. Okay, and for F1, what you need to remember? The refracted rays are parallel. See, on the right side, you put refracted rays, they are parallel to principal axis. Here also. Draw these 2 diagrams. You write the definitions also for F1 in your own words for convex and concave lens. Main differences, see here, for a convex, the rays of light are coming from F1. And for a concave, the rays of light are appearing to meet at this. Here it is coming from F1. Here the rays of light are appearing to meet, Always for a concave, you have to use the word appear because it's not a real thing. Write the definitions. Amit, can you tell me what is F1 for a convex lens?
F1 is a point on the primary axis of the lens
Principal axis.
where principal axis of the lens where the rays of light originating from it become parallel to the principal axis of the lens following reflection through the lens.
Following refraction, after refraction, not reflection.
Refraction through the lens.
Nathan, tell me what is F1 for a concave lens? Nathan is stuck. Sneha, can you tell me what is F1 for a concave lens?
F1 is a point on the principal axis of the lens such that the incident rays of light appearing to meet at it after refraction from the lens become parallel to the principal axis of the lens.
You're reading what is in the textbook only, right? Okay. Yeah, try to understand and say in your own words, okay, or memorize it. Okay, now since you know what's F1 and F2, first focal point and second focal point, you have first focal length and second focal length. So obviously what it is? What is first focal length? It's the distance from first focal point to optical center. What is second focal length? The distance from second focal length,
Optical center to radius of curvature.
not radius of curvature, focal point, first focal.
Focal point.
Okay, F1 is the distance from first focal point to optical center. Here also F1 is first focal length is what? The distance from first focal point to the optical center. Same way, what is second focal length? The distance from second focal point to the optical center. Here also, what is second focal length? The distance from second focal point to the optical center. Focal length, focal point. Second focal length, second focal point. Okay, note the difference. Focal length is the length and the point is called focal point. Okay, last two words that are here is focal plane. You had focal point. What happened? Practice. What time? It's okay. Focal point is there, focal length is there, focal plane is there. Okay, what's the difference? Focal point is what? That point where the light meets or appear to meet. Focal length is the distance from optical center to that. And focal plane is a flat surface, right? You know what's a plane? A flat surface is called a plane. So if I put a flat surface at F2, that is the focal plane. So if the flat surface is at F2, that's called the second focal plane. If the flat surface is at F1, then that's called the first focal plane. Understand? So look at the definition for first focal plane. A plane means flat surface, passing through the first focal point and normal to the principal axis. If this is the principal axis, the plane will be like this. It will not be like this, or it won't be like this. It will be what? Perpendicular to the principal axis. Do you understand? Same way, what's the definition for second focal plane? It's a plane. It's in my hand. Plane. It's a plane that's passing through the second focal point, which is normal. Normal means perpendicular. Normal to what? To this what? Principal axis. Is everyone clear? What's the meaning of the word normal? Perpendicular. What's the meaning of plane? Flat surface. Only one said that. I'll ask that again. What's the meaning of the word normal? Perpendicular. What's the meaning of
Perpendicular.
plane? Flat surface. Write that down somewhere.
That's
Okay. Write the meaning of that word. We use the word normal so many times. Right? Last chapter was full of normal, normal. Normal means
90 degree.
So what we have seen is if there are parallel rays, listen to this. If parallel rays of light, parallel to what? Principal axis. Where do these rays meet? At that focal point, second focal point. What if these rays are parallel to each other but not parallel to the principal axis? F1 is on the other side where rays never meet at F1. And what am I saying? See, in this first case, the rays were parallel to each other and they were also parallel to the principal axis. They will meet at F2. But now the rays are parallel to each other, but not parallel to the principal axis. Like this. Look at this. This is the diagram. The rays are parallel to each other, but they're not parallel to principal axis. Where will they meet? This is F2. They're not meeting at F2. They're meeting at the focal plane. Means on that same line of F2, they're meeting down here. You understand? If they were parallel to the
Yes,
principal
sir.
axis, they would have met exactly at F2. But since this went up, the F2 came down. Down, but in the same line of where F2 is. Is that clear, everyone? So if the rays are parallel to each other, but not parallel to principal axis, where will they meet?
Focal plane.
Second focal plane. And this is second focal plane again for the concave lens. So here also the rays of light, incident rays are parallel to each other, but not parallel to the principal axis. So they will not meet obviously because it's concave. They will diverge, but they will appear to diverge from a point on the second focal plane. Are you understanding? What if they were parallel to the principal axis?
They
Then
will meet at focal point second.
they won't meet, they will appear to diverge from a second focal point.
Yeah.
Right. But now they're
Convex it will meet.
now they're appearing to diverge from where? Not second focal point, but from the second focal plane. Instead of point,
Second
plane. If they're parallel to
Yes.
principal axis, you say focal point. If it's parallel to each other, then you will say focal plane. Are you understanding this, everyone? There's a lot of theory. Today we're only seeing the theory. The next part of the chapter, we are actually seeing, see, this is the end of the A part. A part is all theory, theory, theory to help you understand how things work here. But the next part of the chapter, you'll be drawing diagrams, which is more interesting. You'll need your scale, pencil. You get your compass also. Okay, next class, please get your compass because you have to draw this and I'll show you how to draw these things. See now how bad it looks. Right? Doesn't look good. But when you draw with a compass, it will look perfect. Okay. Okay. Tomorrow, I will stop now. I want to do a little bit of maths also, but it's okay. We'll stop. And
Yes,
next,
sir.
tomorrow also you have practice or what? What time? It's okay. You can go a little late. Okay. You're just following everyone. Oh, you're the leader, no? You're standing in front. Huh? Okay. So tomorrow, what you'll bring? Bring your compass, scale, pencil. 3 things very important. And we will continue with this chapter and also bring maths. We will start with the new chapter in maths. Okay. All right. So this is the B part of this chapter. We're seeing all the rays the rules to draw the ray diagrams. So on the left side, we have 3 rules for convex lens, and on the right side, we'll have 3 rules for the concave lens. the first rule for a convex lens is if a ray of light travels through the optical center. This is the optical center. If a ray of light travels through the optical center, what happens to the ray? It does not deviate. It keeps going straight in the same way. Right? We had seen this yesterday also. Okay, this is one rule. The same rule can also be applied for a concave lens. Okay, if a ray of light is coming towards the optical center, it will keep going the same way without any deviation. Right. Yes, and by the way, points. Okay, now we have F on both the sides. Okay, for a convex lens, what's on the right side? F2 is on the right, F1 is on the left. Okay, the second law is the second law is if a ray of light is parallel to the principal axis, what will happen to this ray? It will go through F2. Remember, we saw this diagram also yesterday. So this is just mentioned as a law. The second, the third one is if a ray of light is passing through F1, then what's going to happen to this ray? It will go parallel to the principal axis. Okay, these are the three ray diagrams that you need to know how to draw for a convex lens. Okay, the first one is if a ray of light is passing through the optical center, it will keep going straight, no deviation. Second, if a ray of light is parallel to the principal axis, after refraction, it will go through F2. And the third one is if a ray of light passes through F1, after refraction, it will go parallel to the principal axis. Okay, now similarly on the concave side, the first one we have drawn, if a ray of light is passing through the optical center, it will keep traveling without deviating. Second one is if a ray of light is parallel to the principal axis, what will happen to this? So here we have F. What is here? Okay, on the left side we have F2, on the right side we have F1. F2, F1. Okay, so what will happen to this ray now? Parallel to the principal axis. Will it go through F1 or it will go away? It will go away. But how? Which direction? It will go as if it is coming out from where? F2. Okay. So you keep your scale. How you'll keep your scale? Like through F2 and that point. See, like this. Understand? Scale from F2 to that point where the incident ray met, and then you draw dotted lines till on the left side. On the right side, you'll draw a solid line. Okay. Now let's apply that law here also. Here, how it is, the ray is coming towards F1. Okay, look at this. So the ray is as if it is going straight towards F1. So what will happen to this ray? It will go parallel to the principal axis. Is that clear? So these are the 6 ray diagrams that you have to learn to draw, and then you can use this to draw any diagram. Okay.
So just a straight line, no?
Parallel to which one?
Yeah, the third one.
Yeah, it will be the refracted ray will go parallel to the principal axis.
So Anna, do they have different names for each diagram?
No, these are just the laws that you will be using. Okay, first law is where the ray passes through optical center. Second law is where the incident ray is parallel to the principal axis. And the third is where the refracted ray is parallel to the principal axis. Okay, so to draw this, first you will draw the principal axis. On the principal axis, this is to draw any ray diagram, okay? You will mark these 5 points, okay? If it's a convex lens, then you have your F1s on the left. If it's a concave lens, you will have your F1s on the right. So on the left, you have F1 and 2F1. 2F1 means double of F1. And on the right side, you have F2 and 2F2, which is the double of F2. Now, this 2F1 and the 2F2 are actually the center of curvatures. Okay, which means it's the center of the circle. So whenever you're drawing a circle, you always keep the point at the center of the circle, right? So in the same way, you will keep the compass, the pointed part at 2F1. And with the pencil, you'll keep here, and then you will make an arc like this. Okay, It will be a very gradual arc, something like that. Okay, same thing you do on the other side. Okay, you keep your point at 2F2 and then make an arc on the other side like this. Is everyone clear how to draw the lens? Okay. Now, what about the concave lens? Same thing. You'll
Now,
draw.
how do we draw the lens once again?
You'll keep the point at the 2F1 and make this first arc, the right side arc. See, first you'll draw the line. Okay, you'll draw this line from top to down. You'll draw this line first. Okay, so then keeping the center at 2F1, you'll make an arc for the right side of the lens. Keeping the point at 2F2, you'll make the arc on the left side. That is the left side of the lens. Is that clear, everybody? Okay. Now for a concave lens, same thing. Again, you will mark these 5 points. Okay. So what's the center point? That is optical center. What's on the right side now? F1, and the next one is 2F1. On the left side, you have F2 and 2F2. So here also you'll keep the point. Oh, before that, you will draw this line here. Okay. Now you'll keep the point here at 2F1. And now you'll somewhere over here, just draw a small line like this. Okay, do this. Okay. And keeping the point at this point, you will make an arc like this. See that the arc doesn't cross and go that side. Something like this for the left side. Then keep the point on the right side on 2F1, and then from here make an arc on this side. Is that clear how you'll draw it? Okay, you will get a proper shape because it's very hard to draw with this. Only this much of this is working, so I don't get proper circles. Okay. Anyway, that's how you will draw it. Any doubt in this? Okay. Now to draw objects. Okay, how do you draw the object? Okay, I'm drawing the object separately over here, and then I'm going to place it. Okay, so your object is always drawn as an arrow. Now the object can be placed anywhere on the principal axis. Okay, the object should not be floating up like this. It should not be sunk underneath the principal axis. Think of the principal axis as the ground, and so this will be resting on the principal axis. You have drawn like these diagrams last year also, and I think 8th standard also, if I'm not mistaken. Okay, so yeah, you'll draw this. Now you'll keep this object at any point that you want. There are 6 points totally. Okay, the first point would be infinity. Object is at infinity. The second point is where the object is here, that is beyond 2F1. Then the third diagram is where the object is at 2F1. Then fourth diagram is here between F1 and 2F1. Then the fifth diagram is at F1, and the sixth diagram is here between O and F1. Okay, so like that you have 6 diagrams for the convex lens. Okay, we'll see concave after this. Now let's place it anywhere. Okay, suppose I place it over here. Okay, how will you draw the rays? Now previously we saw 3 different rays can be drawn. Right, what are the 3 rays? First ray can be drawn through optical center, next ray is parallel to principal axis, and next ray passes through F1. These are the 3 rays that you can draw. Now out of the 3 you can draw any 2. It's your choice which 2 you want to draw. Okay, all right, so first one we'll draw the easiest. Which is the easiest one? Huh? This one, right? Through the optical center. That's the easiest because it's just one single line. There's no bend, no nothing, right? So you will draw that as the first ray. Now second ray is your choice. Should you either go parallel to principal axis if you want, or you can go through F1. 2 options are there, right? So say I draw the one parallel to principal axis. Okay, so this will come here, and now what will happen to this ray? It will go through F2, correct? If you notice, see these 2 rays, they will meet. Somewhere they'll meet. Okay, so here this is meeting somewhere over here. Rays will always meet each other. If they don't meet, then that means the rays are parallel to each other and they are meeting where? Infinity. If they don't meet, it means they are meeting at infinity. Okay, so this diagram is like this. How would be the third ray? The third ray is how? Go through F1. Okay, it's going out of my lens. Okay, but say the lens is there. You see, the third ray also should meet exactly at the same point where the other 2 rays met. Okay. If it doesn't meet there, that means you have done something wrong in the spacing between these 5 points, or your line, this line here is not perpendicular to the principal axis. Okay. So just make sure that all your lines are parallel and perpendicular and everything, however it's supposed to be. Is that clear, everyone, how to draw ray diagrams? Any doubt? Okay, so what we have drawn is where the object is placed where? Between F1 and 2F1. Now the object will be called something. We'll name it. So we'll call this AB. Okay, A is the upper part and B is the lower part. You see, we have only drawn rays for the point A. We have not drawn any rays for the point B. Why is that? Because B is on the principal axis, and if we draw any ray also, see, suppose I'm drawing a ray from B passing through optical center. It's going straight only. Suppose I draw a ray passing through F1, passing through F1. Like, you can't do any ray. If I'm drawing a ray parallel to principal axis, that also will be the same thing. You see, all the 3 rays that I draw will be on the principal axis. So there is no point of drawing any ray from the point B. You will only draw rays from the point A. And how many rays will you draw from A? 2. You can draw 3, but you don't need 3. You just need 2. Why do you need 2? Why not just 1?
You need to show that the lines are meeting.
Yeah, lines have to meet, right? If you have only one line, it doesn't meet anything. So you need 2 lines to show where the 2 lines meet. Okay. All right, draw this. Show me. Paper. How many centimeters you took the gap is? 2. That's 2 over. So 2 is a little small, right? So 3 is good, I think. How much you took? 3, no? Yeah. So I think 3 is a good size, okay? Between every point, you take 3 centimeters. Yeah. And there's one thing which I forgot to mention is you have to draw the image, okay? Where will you draw the images? Where the points meet, where the rays meet. So the rays are meeting at this point. That is where you will draw the image, okay? Like this. So the arrow part, the A comes to this lower part here. See what happened to the image? It became inverted. So that point we'll call it A dash. And the top point here we'll call that B dash. Okay, see here. Now we have only drawn one diagram for the convex lens. There are totally how many diagrams we saw? 6. Okay, 6 diagrams are there. So we'll go through them in the textbook and we'll draw whichever is necessary. We won't be drawing everything. You have to do that as your homework. Okay, draw all the 6, practice them. So what are the properties of the image that's formed here now? There are 4 properties for this image. What are the properties? First property, talk about where is the image formed? Okay, where means on the principal axis at which point? Is it between O and F2? Is it between at F2? Is it between F2? Okay, it's beyond 2F2. That is the first property, okay? Formed beyond 2F2. Next, now any image that's formed on the right side, listen very carefully, wait, don't write it. Any image that's formed on the right side will be inverted. Okay, and these inverted images are called real images. Real means they are formed on a screen. They are actual rays meeting at a point and it is formed on a screen. If you put a screen over there, you will see the image formed over there at AB. Okay, so these are 2 properties we have seen. One is if it's on the right side, the image will be real and the image will be inverted. Okay, so that is your second and third point. Second point is it's real. Third point is inverted. Okay, fourth point, you talk about the size. What happened to the size? If you compare the object and the image, what happened to the image? It got enlarged, right? It became bigger. So you write enlarged. Okay, write down these 4 properties for this. Okay, For the second diagram, I want you to place the object beyond 2f1. Okay, draw the same convex lens, and this time the object, where is it going to be? Beyond 2f1. So that means this will be somewhere here like this. Okay, follow the same rules and draw any two rays, and try to do it a little more faster this time. Okay, try like maybe 3 minutes. Okay, and keep a 3 centimeter gap this time, Beryl, between every point. Okay, you'll get a better diagram. The ones at home, I didn't see your diagrams. Did you all send it? No one sent it yet. Okay, send it first. Send it and then go to the next. I'll give you 1 minute to send it. And rejoin the meeting. Okay, now when you learn and go through all the 6 different diagrams, you will notice something. Okay, what that is now we are starting where the object is at infinity, and now the object is getting closer to the lens, right? What happens to the image at the same time? As the object is getting closer to the lens, the image will go farther away from the lens. Okay, so first, in the first diagram where the object is at infinity, where is the image going to be formed? You know, yeah, see, this is the diagram for that. When you're drawing the object at infinity, you can't draw the object because it's at infinity. So you will just draw 2 parallel lines. You're using only that one rule. 2 parallel lines. Those 2 parallel lines will meet at f2. So that means at f2 you will get the image. Okay. So here, when object is at infinity, where is the image formed? At f2. What are the properties? Is they're real, they're inverted, and how it became very small. Okay, so it's highly diminished, not just diminished. Okay, so this is the closest point where the image can be to the lens. Now, as the object comes closer to the lens, the image starts going farther away. Okay, the second diagram is what you just drew right now, where the object is beyond where? Object beyond 2f. So that time, where is the image formed? Yeah, where was the image formed? Between f2 and 2f2. In the third diagram, the object comes a little more closer. Comes to where? 2f1. And where will the image go now? It will go ahead, it will go to 2f2. Okay, so if object is at 2f1, image will also be at the same distance, 2f2. Now, the next, when the object is here, that's what we drew first. The image goes a little farther away, goes to beyond 2f2. Fifth diagram, where the object is at f1. Now, where will the image go? Infinity. You can't draw the image. Okay. And then the last diagram is where the object is here between O and F1. Now, where will this go? Can't go more farther away. It already went to infinity. So here, what's going to happen is the rays will go in such a way that the image will be formed on the same side. And it won't be an inverted image. It will be an erect image. Okay, we're going to draw these diagrams. Don't worry. But this is how the different diagrams are. Okay, I'll just revise with you once again. The first diagram where the object is at infinity. Where is image going to form? At f2. Second diagram, the object comes where now? Beyond 2f1. So the image goes little away. Here it goes. Where? Between f and 2f. Next, the object comes a little more closer. It comes to 2f1. Where does image go now? At 2f2. Next, the object comes a little more closer. It's between f and 2f. So the image is formed beyond 2f2. Next, fifth diagram, the object comes to f1. Where will the image go now? Infinity. And the last diagram, the object is here between O and f1. For this diagram, the image won't be formed on the right side. It will be formed on the left side. Okay. And when image is formed on the left side, it is not real. It is unreal. Unreal is called virtual. And also they won't be inverted. They'll be erect. That means the arrow will be pointed upwards. Is that clear, everyone? Okay, so now which one do you want to draw? Last one, this one, where the object is between O and F1. Okay, all right, start drawing. Don't draw a very big object because the image is going to become enlarged and you won't have space to draw it. Okay, so draw something like this. Okay, how do you draw the rays for this diagram? First ray, how you drew? Tell me. From the head, where to draw it? Parallel to principal axis. And this goes through F2. Next ray, how will draw? Through optical center. Correct? So now you can see both these rays, they're going away from each other, which means they will not meet on the right side. Where will they meet? They'll meet on the left side. So you extend these two rays to the left side with a dotted line. Okay. So take your scale, keep it on the same direction as how the ray you've drawn, and then you extend it backwards with dotted lines. Like this. Got it? Then do the same thing for the other ray also, extend it backwards. Okay, so the ray meets anywhere on the left side. Okay, it doesn't have to be between F1 and 2F2. It can be anywhere, but it'll be on the left side. Okay, so this is your image. Now the image that you draw, also draw dotted line image. Don't draw solid line. Okay, put a dotted line because it's not a real image. It's a imaginary image, virtual image. So your real image, I mean your object, sorry, is called AB, and this will be A dash B dash. Now what are the properties? First property, where is it formed? On the same side, or yeah, on the same side as of the object. Second one, real or virtual?
Virtual.
Virtual. Now all virtual images will be inverted or erect?
Correct.
Erect. And fourth one is the size. What happened to the size? Enlarged. Okay, so these are the four properties when the object is placed between F1 and O. Now you have also applications. Where do we use the lens in such type of a way? Okay, where do we keep when we keep the object so close to the lens like this? A magnifying glass. You all know what's a magnifying glass? Okay, so in a magnifying glass, we keep the object like at a point between O and F1, right? And when we look, what happens to the image? It gets magnified. See, the image is magnified here, enlarged. Okay, so this is how we use a magnifying glass. What if we keep it in like the other diagrams that we just drew here? If we keep the object so far away, what's going to happen? If I keep the object so far away, what's going to happen to the image? It's going to get inverted. Have you ever looked through a magnifying glass and seen inverted? That's because the inverted image is not happening on the same side. It's happening on the side of your eyes. Look, if I'm looking through the magnifying glass, the object is on the side, front of it. Where will the image be formed? On the side, no? So I think you might be able to, I don't know. Yeah, actually you can. See, like if you try to look, when you keep the magnifying glass away from your eyes and see, no, everything looks inverted. Yeah, you can actually see it because the image is forming inside your eyes. Object is in front of you. Where's the image forming? Inside your eye. So you can see it inverted. Just take this and look at something far away. You will see it is inverted. Pass it on. Take the magnifying glass and you look at something far away. Is it inverted? Yeah. Okay. So this is what is happening. You're placing the image, sorry, the object beyond F1 or anywhere beyond F1. If it's in front of F1, that's the time you will see an erect image. Like my hand is, it's erect and it is enlarged. Okay, now looking at your textbook, see all the different diagrams. Okay, so this first
Is it
diagram,
the same when we use the binoculars?
binoculars also similar thing is happening, but your object is yeah. In binoculars, what's happening is this one. Right. So in binoculars, it's not just one lens. Okay, there are multiple lenses because one lens will not do the work. In binoculars, you generally look at something that's very far away, which is at infinity. Now, at infinity, what happens to the image? When the object is placed at infinity, what happens to the image? Enlarged? No, it becomes diminished, highly
The image
diminished.
is small.
Yeah, it becomes highly diminished. Then, so what's the point of having a binocular if everything is getting diminished, right? So they don't use a single lens in a binocular. They use two lenses, and those two lenses will somehow magnify the image. Okay. Yeah, it's a complex diagram for a binocular, but somehow it magnifies the image. Okay, they place the lenses in such a way. A camera, like even a phone camera, which is so tiny, it has like 5 or 6 lenses in front of the sensor. Okay, so they place so many lenses in front so that each lens will do something to the image and you will get a proper image. In your book, I think you have different applications of each of these. Okay, so let's see that. The first diagram is where the object is at infinity. The image is formed at focus. See, the application is here. In this manner, a convex lens is used either as a burning glass or a camera lens. Have you tried burning paper with a lens? No? When you tried it? If you have a good magnifying glass,
Yeah.
not a very good one, because I tried burning, nothing happens. Okay.
Yes.
If you have a nice magnifying glass, you point it like allow the sun's rays to pass through it. And this is what's going to happen. All the rays, sun's rays, which are parallel beams of light, they will all meet at the point F2. So at F2, if you keep a paper, the paper is supposed to burn because all that heat is all converging at that one tiny point. Right. So there's too much heat being formed at that one point and a paper can burn. Okay, this lens, it doesn't get the light to one point, it just makes a circle, which means it doesn't have a proper, it's not a proper curve. If it's a proper curve, then you have one single point as the focus. This one doesn't have that. Okay, we used to burn eucalyptus leaves and all, dried eucalyptus leaves, because that's easy to burn. Paper, it takes some time to burn. Okay, and it's also used as a camera lens. Even binocular lens, they use it this way because whatever you're looking at is at infinity. Okay, the case 2 is what we drew, what you all drew by yourself. The object is at beyond 2f1. Okay, so here, what are the applications? A convex lens used in this mirror, used in this manner, is a camera lens when the object is not very far. See, when you're taking a photo with a camera, your object could either be at infinity, it could be closer, it could be at different places, right? So that's why you can use camera lens as any answer. Example for anything, you can say camera lens. Next, case 3 is where the object is at 2f1. Where is the image going to be formed? At 2f2. This is the hardest diagram to draw because your image needs to form exactly at 2f2. If you make some mistake, your image will either go a little front or a little back and it won't form at 2f2. So here you have to do some little adjustments to get your image to the right point. Okay, everyone? Okay, so where is it used? In this manner, a convex lens is used as a terrestrial telescope for erecting an inverted image formed by the objective lens. So as I said, like just like a binocular has two lenses, even a telescope is also like a binocular, right? But only one eye. So even this telescope uses two lenses. One lens is called the objective lens, and the other lens is called an erecting lens. It turns it upside down. So one lens is for magnifying, other lens is for making it, for inverting it. So this is how they invert an image. Because size is not changing. It is just doing the work of inverting the image. So that's where we use the lens in this manner. Next, the first diagram that we drew where the object is between f1 and 2f1. So here the image is inverted, upside down, real, and little enlarged. Okay, where do we use this? Here. In this manner, a convex lens is used in cinema and slide projectors. Here, the magnified image is obtained on a screen placed at a large distance on the other side of the lens. Care is taken to put the slide of or film in front of the lens just beyond its focus in an inverted position so as to obtain an erect and magnified image on the screen. Okay, so a projector. This is how a projector works. See, a projector is magnifying it, right? The farther you take the screen away from the lens, what happens to the image? It gets bigger and bigger. Okay, so you need to place this object exactly just a little bit beyond f1. It should not be at f1. If it is at f1, what's going to happen? Where's the image going to form? At infinity. So you'll not get a clear image. You want the rays to meet at the screen. It should not meet at infinity, then you'll not get a clear image. So the object has to be where? Just beyond f1, not right in between. Then what will happen is you won't get a very magnified image. It will be small. The closer you come to f1, the bigger your image will get. In front of every projector, there is a adjusting thing. One is to zoom and one is to focus. Okay, so what you're doing when zooming and focusing is you're moving the object closer to f1 or away from f1. That way you can get a clear image at the certain point where you want it to form. What happened, Beryl? What is so funny? Laugh it out. Okay, so this is a projector. Now also you notice the image gets inverted, right? So whatever you're placing in the projector is actually inverted so that when it comes on the screen, it turns straight. You know, there is these other projectors where you have to place a paper inside. We don't see that nowadays, but when we were small, you have to write on a plastic sheet with a pen, and you put that plastic sheet on one light source, and that light will hit on a mirror and it will project up. So whatever you have written on that plastic sheet, you can see it on the screen. That was like the old projectors, where they did not have these digital projectors where you can watch movies and videos. Only what you write on that paper, you can see it over there. So in that, you have to place the image object inverted so that it will become erect on that. Okay, the next one is where the object is at f1. Here where, see how the diagram is? Look at this. Two rays you are drawing, and both the rays are parallel to each other, which means they will not meet, or they will meet at infinity. So here, since they meet at infinity, okay, principal axis is going straight, the two rays are going parallel like that over there. So the image that you get will be extremely large, okay, highly magnified image. In this manner, a convex lens is used in the collimator of a spectrometer to obtain a parallel beam of light by placing the source of light at the focus of a convex lens. Something like a laser. Okay, like if you want to get parallel beams of light, so you place the object at that certain point, then the rays that you get will be parallel. You know, like in a laser also, the rays have to be parallel to each other. Otherwise, the laser light will go away from each other and it will become dim. Have you used a laser?
Yes.
You know what's a laser light? No? Point will form no like that. Okay, so the laser light, the source is made in such a, I mean the rays are made in such a way that they are parallel to each other. That way the thin small point will travel for a very long distance. Even if you move it like half a kilometer away, you'll get one small point. Okay, that's how a laser is. So I think they use it like this. Last one is where the object is where? Between F1 and O. That's what you drew. And where do we see this? Where do we use this? As I showed you in a magnifying glass or a simple microscope. Magnifying glass is like a microscope, right? To form a magnified virtual image of a tiny object such as a small letter of a book or a small part of a watch. Basically, you can zoom with it. All right, so in the convex lens, let me just summarize. How many diagrams did we draw for convex lens? How many are there? How many are there? 6 are there. From these 6, how many of the diagrams you get real images? 5. The first 5 you get real images. The last one which you drew last, in that you're getting a virtual, erect and virtual image. Okay, now about size. The closer anything is, the object or the image, the closer it is to the lens, the smaller it is. The farther you go away from the lens, the bigger it is. You understood? So in this diagram, first diagram, Which was closer, object or image? Object is closer to the lens. That means the object is smaller and the image is larger. In the second time that diagram that you drew, which I did not draw, the object was here beyond 2f1 and the image was closer here. In that, see what happened. Which was bigger? Object was bigger because it's farther away and the image was smaller. That's why we say diminished. Okay. This diagram that we drew, this is different. Okay. That rule that I said works for real images. When object is on the left and image is formed on the right. All right. Physics will stop. We'll just do 5-10 minutes of maths. Okay. Take maths. There are a few more diagrams for the concave, but that we'll do in the next class. The convex, we have seen all the diagrams. When you go home, you will practice all the diagrams. All the 6 diagrams. Draw it and practice. Okay, Beryl? Okay, how do we're going to see for a concave lens, you don't have 6 diagrams, you have only 2 diagrams. Okay, and the last class we saw how to draw the ray diagram. How do we draw the ray diagram? First, what we have to do? What's the first step? You'll draw the line. What is this line called? The principal axis. On the principal axis, you will measure with 3 centimeter gap. You will measure points. Okay. Now on the left side, okay, center we have O, which is the optical center. What do we have on the left side here? F1 or F2? F2. For a convex lens, left side was F1. But for a concave lens, left side is F2. And this point is what? 2F2. That means double of F2. On the right side, we have F1. And this is double of F1. So that is 2F1. When you're drawing it, you'll use your compass, put the point at 2F2. Before that, you will draw this line that passes through O. Okay. All right. So now you'll put your point at 2F2 and then don't keep the pencil here. If you keep the pencil here, what shape you'll get? You'll get a convex lens. Put the pencil over here somewhere and then draw. So you'll get a concave. Okay. Now put the point on the other side, 2F1 side, and there also you will draw this. Okay. And so that's how you get your concave lens. All right. Now the first diagram is where the object is at where? Infinity. Okay. Object is at infinity. So you cannot draw the object. So you just draw 2 parallel lines. Okay. Now first line, where is it going to go? Up, down. It's going to go up as if it is coming out from where? F2. Okay, that's the ray. The second ray also, it goes and it goes out as if it is coming out from F2. Okay, put a scale and draw a nice straight line. Dotted lines on the left side, a solid line on the right side. Okay, so where is the image formed? The image is formed where the 2 rays meet. And where are the 2 rays meeting? At F2. So that's where your image is going to be formed. So what are the properties of this image? It's forming at a point, so it will be highly diminished. Diminished means it became smaller. But if it's so small like a point, what we say? Highly diminished. Is it virtual or real? Virtual, because it's on the same side as that of the object. If the image is found on the left side, it is virtual and erect. If it's on the right side, it is real and inverted. So this is virtual and erect. Okay, so those are the properties. How many properties do we have? 4 properties. What are the 4 properties? First property is what? Where is it formed? Formed at F2. Or same side, you can say whatever. But the point is, where is it formed? You have to mention F2, F1, between this, beyond. This is formed at F2. Second, real or virtual? Virtual. Third point, if it is virtual, it will be erect. Fourth point about the size. How's the size? Highly diminished. Okay, draw this quickly, everyone. Oh, sorry. Yeah, image. See in your book how they have mentioned the points. If the object is at infinity, where is the image formed? At the focus. I've written at f2. Here they have written at the focus on the same side of the lens as the object. I didn't write same side because it's understood that f2 is on the same side, on the left side. Okay. Then virtual upright. Instead of erect, they have written upright. It's the same thing. Highly diminished. Application is in a Galilean telescope. Okay. You don't have your instruments today? Then just draw a rough diagram. Use a scale. I mean, use a pencil and scale. At least you have scale. I'll give you scale if you want. You have scale? Do. See, I'll do one thing. Listen, everyone. Before you draw, Nathan has to leave. I'll just explain the next one also in 2 or 3 minutes, and then you can draw it. Okay. So just listen. Nathan, you're there?
Yes.
Okay. Now this is the same diagram, but here the image is at infinity, but it is not parallel to the principal axis. You can see the two rays are coming from top somewhere, but the two rays are parallel to each other. They're not parallel to principal axis, but they are parallel to each other. Okay, so the first ray will draw it straight towards the optical center. That will keep going straight without any deviation. The second ray is pointed straight to f1. So what happens to this ray after refraction? It becomes parallel to the principal axis. Okay, that's one of the rules, right? If a ray of light is pointed straight to f1, it will refract. It will go away from the path and it will go parallel to the principal axis. Now these two rays, where do they meet? You extend them backwards and they meet at the focal plane, not at the focus, but at the focal plane. Focal plane is that flat surface, right? At f2, that's where the image is formed. Same properties as before, is just another way to draw the same case. Instead of drawing two parallel lines to the principal axis, you're drawing two parallel lines that are not parallel to the principal axis. Is that clear? Okay, I'll give you time to draw it. And look at the last one. Okay, I'll explain in detail in a few minutes, but now just for you to understand, here the object is anywhere in front of the lens. It doesn't have to be at 2f2 or between this or at this. Where is the object placed? Anywhere in front of the lens. So two rays have to be drawn. The first ray is how? Through optical center. Second ray will draw parallel to principal axis. How does the ray go? Converges or diverges? It diverges as if it is coming out from f2. Okay, so you see your two rays, one is going up there, one is going down here. Where do they meet? Extend them backwards and they meet at this point here. So that's where your image is formed. So what are the properties of this image? First of all, where is it formed? Between O and f2. Remember in the first diagram, where was the image formed? In this one, where was the image formed? At f2. But now when the object came closer, what happened to the image? It went closer to the lens. And so it has to be between O and f2. Next, real or virtual? Virtual and upright or erect. And size, what happened to the size? Diminished, not highly diminished, just diminished. Okay. All right. So that's all you have for these diagrams. Yes. Now you can draw. Nathan, if you have to leave, you leave. If you don't, then you draw this diagram. Done? So now we'll draw the one where the object is anywhere in front of the lens. Okay, I'll just show you once how to draw. You see the steps and then you draw by yourself. Are you all still drawing the previous one? Done? Done? Clear? Done? Okay, so what is the first one? Tell me now. First ray from where? Optical center. Always first ray is the easiest one through the optical center. Okay, second ray, you can either draw through F. No. It has to be straight. You can't draw through this. Okay. What are the options here actually? If it goes straight, if the ray is parallel to the principal axis, it will go away as if it is coming out from F2. What was the other diagram? Oh, if it's pointing straight towards F1, then it will go how? It will go parallel to principal axis. Okay. So we can do that also. Point it straight to F1 and then it will go parallel to principal axis. Okay, but we won't draw that ray. What the one that we'll draw is the one that's parallel to principal axis. How will this ray go? Huh? As if it is deviating or coming out of F2. So keep your scale like this. On the left side, you will draw dotted lines. On the right side, you will draw a solid line. Okay, so these are your two rays. Now they're deep, they're going away from each other. Where will they meet? Extend them backwards. The lines are already there backwards. You don't have to draw new lines. So this is the point where the two rays are meeting. That's where you will draw your image. Is everyone clear? Okay, so if your object is named AB, your image will be named A dash B dash. Okay, draw this and write down the 4 properties of this. Done? Draw and then show me. Okay, and then we'll end. I'm writing the properties here. All right, I hope you're done writing. See, there are 2 ways of writing the first point. Where is it formed? You can just say between O and F2. Or you can say focus. Which focus? The focus on the same side as that of the object. So in your book, that's how it's written. So I've written like that. Where is the image? It's formed between O and focus on the same side as that of the object. Then virtual, you know, upright, you know. Anything on the left side is virtual and upright. And then diminished. So this B part of the chapter is done. Now what is remaining is 2 formulas and 1 experiment. Okay. All right, we'll end with this.